Tiny farm road cuts straight across the pale fields of central Turkey, then stops at an edge that did not exist before. Beyond it is a circular void with walls dropping through soil and limestone. In one January 2025 collapse near Altınöken, the opening reached roughly 50 meters across, and a witness recorded part of the rim breaking away while dust rose from the ground. The field looked quiet, the ground was still moving. That image is becoming harder to treat as an isolated accident. Across the Konya closed basin, official mapping has recorded hundreds of sinkholes in Konya, Karaman, and Aksaray. Most are concentrated around Karapınar, but they are no longer confined to one famous cluster. New collapses and broad zones of subsidence have appeared in places where this kind of failure was once rare or undocumented. What looks from above like a scatter of holes is beginning to behave like a widening sinkhole field, and official counts can appear inconsistent because researchers do not always count the same feature. One inventory may include only deep, abrupt collapses. Another may include shallow sags, fissures, and broader, subsident structures. In earlier surveys, adding small depressions and surface cracks pushed the regional total far above the number of classic vertical sinkholes. And for this documentary, the safest current anchor is the AFA classified inventory released in December 2025, while the larger historical estimates remain context rather than interchangeable totals. The geographic spread is equally important, and Karapınar contains the overwhelming majority of mapped holes, yet AFAD records now extend through districts including Seyhanbeli, Sumra, Karate, Altınöken, and Ereğli. In separate reporting between May 2024 and May 2025 described 20 new sinkholes across Konya, Karaman, Aksaray, Afyonkarahisar, Ser, Sivas, and Eskişehir. And that does not prove one underground cavity system connects all of those provinces. It shows that the visible hazard is no longer a single local curiosity in one district. And from the air, some farms contain several holes within the same set of property lines. The spacing is what turns an isolated collapse into a field. One dark opening, another beyond the irrigation track, then a shallow depression where crops grow unevenly. Each feature may have its own roof and cavity, but together they reveal a corridor of susceptible ground. The obvious explanation is drought. Central Anatolia is dry, irrigation demand is intense, and groundwater has fallen sharply. But drought alone does not carve a vertical shaft into a wheat field. And the deeper answer lies in the combination of soluble rock, buried cavities, falling water levels, faults, old lake sediment, and the sudden transfer of weight through a roof that may have been weakening for years. That is why the newest hole is not the full story. And the more important question is what is happening in the ground between the visible collapses. By late 2025, an AFAD susceptibility mapping effort had recorded 684 sinkholes across the wider closed basin, including 655 in Konya province, and 504 were in Karapınar, but others had been identified across 11 additional Konya districts. The inventory separated them into different mechanisms: abrupt cover collapse, slower cover subsidence, and bedrock collapse. And those categories matter because not every sinking patch becomes a dramatic crater, and not every crater forms in the same way. Still, the numbers show a regional pattern. A major 2026 study reconstructed sinkhole development across about 50,000 square kilometers of the basin from 2000 through 2024. And the documented formation rate rose from roughly 3 sinkholes a year in the 2000 to 2010 interval to about 32 a year during 2016 to 2019. Since 2020, the rate in that inventory declined to about 22 a year. That is not an all clear. It means the system remains active at a high rate, even though the trend is not a simple line that climbs every year. The same study found that new sinkholes strongly cluster near earlier ones, especially along fault zones. And a simple 500-meter buffer around sinkholes, documented from 2011 to 2019, captured about 65% of the new sinkholes that appeared from 2023-23-24Y, while covering only a small fraction of the basin. In other words, the old holes are not merely scars. They are clues to where the subsurface is already organized for future failure. Stay with me, because that does not mean a scientist can point to a circle on a map and name the day it will open. Susceptibility is not prediction. It is a way to narrow a vast landscape into smaller zones where the geology, groundwater, and collapse history deserve much closer attention. That distinction becomes vivid in Karapınar, and in January 2025, another new sinkhole opened in the Hotemiş area. Measuring about 8 meters across and 25 meters deep, nearby residents said 2 much larger holes already existed within the same local area, and the new collapse did not create the regional hazard. It revealed another piece of it. The title of this story says, "A new sinkhole field is opening across central Turkey." The strongest defensible meaning is not that one continuous trench is tearing across the country. It is that active clusters are expanding across the Konya closed basin. Recent sinkholes are appearing beyond the best-known core, and satellite measurements show the ground sinking between some of those sudden failures. And to understand why, Picture the surface as the last intact layer in a much older underground structure. Beneath the crops are lake sediments, limestone, clay-rich layers, fractures and cavities shaped by water over long periods. And the roof can look stable from above while support is being rearranged below. Then one change crosses a local threshold. A tractor does not need to create the cavity. A rainstorm does not need to create the cavity. May pumping, well, does not need to sit directly beside the final hole. Each can become part of a chain that began before anyone saw a crack. And once that chain is visible, the sinkhole stops being a single event. It becomes evidence that the landscape itself is changing. The Nakania Closed Basin is a broad interior depression with no normal river outlet to the sea. Water arrives through precipitation, snowmelt streams, and groundwater recharge, then leaves mainly through evaporation, pumping, and underground pathways. And that closed geometry helped create fertile plains, wetlands, salt lakes, and one of Turkey's most important agricultural regions. It also made the basin extremely sensitive to a water balance that no longer closes. And under much of the region lies the Insuyu Formation, a package of limestone, clay limestone, dolomitic limestone, marl, and related layers. Water moving through fractures can dissolve carbonate rock, over time opening and enlarge into channels and cavities. Some remain deep in bedrock, and others sit beneath loose alluvium or old lake sediment, hidden under fields that appear perfectly flat. A classic collapse sinkhole forms when the material above one of those voids can no longer bridge the opening. Soil and sediment begin to migrate downward. The roof arches, fractures, and thins. And at first, the surface may sag by millimeters or centimeters. Eventually, a small section gives way, loading the material beside it. And failure can move upward through the cover until the final roof reaches the surface. The last step can be sudden, but the preparation is usually not. And groundwater changes that process in several ways. When an aquifer is full, water pressure supports grains and reduces some of the effective load carried by the sediment framework. Heavy pumping lowers pore pressure, allowing compressible layers to compact. Falling water levels can also expose cavity walls and roofs that had been partly supported by water. At the same time, changing hydraulic gradients redirect flow through fractures and carry fine material into openings. None of those effects means pumping alone creates every sinkhole. And the rock must be susceptible, the geometry must allow a cavity or a weak zone, and local triggers vary. Yet the scale of groundwater withdrawal in the basin is impossible to ignore. Research has described tens of thousands of registered wells and a much larger number of unregistered ones. A 2025 governance study concluded that groundwater levels in the basin had declined nearly 30 meters as crop patterns, irrigation demand, and weak enforcement sustained overuse. And farmers are not pumping because they want the land to fail. They are pumping because crops need water in a dry climate and surface supplies are limited. That is the contradiction at the center of this disaster. The water that keeps the field productive can also help remove support from the ground beneath it. And the most powerful evidence comes from places where collapse is no longer confined to a visible hole. At the former Akinkel wetland, satellite radar measured average subsidence of roughly 15 to 30 millimeters per year from 2014 to 323. Nin, some locations. Total downward movement approached 23 centimeters over 9 years. And those numbers are small compared with a 25-meter deep crater, but that comparison is misleading. A sinkhole is the final break in a local roof. Subsidence is the larger field of deformation that may surround or precede it. There are also two very different ways the surface can descend. Broadland subsidence happens as aquifer sediments compact across a wide area. It can tilt canals, strain roads, and alter drainage without producing a vertical wall. And cover collapse is concentrated and abrupt, as loose material drains into a cavity until the surface roof breaks. One process can increase the conditions for the other, but a satellite map of sinking ground is not automatically a map of tomorrow's craters. And the old lake deposits around Akagul make that distinction visible. Fine sediment can compact as groundwater pressure falls, while buried limestone boundaries and fractures create specific places where runoff can focus. A person standing there may see only a shallow basin after rain. Radar can see a multi-year deformation pattern, and field mapping can reveal that recent holes line up with structural weaknesses. Akagul matters because recent cover collapse sinkholes appeared in an area where they had not previously been documented. The wetland had dried and changed over decades while groundwater extraction, old lake deposits, fault-controlled flow, and seasonal runoff interacted beneath the former shore. Researchers found the strongest sinking in the southern part of the wetland near the boundary between limestone and alluvial sediment. During intense rain, water can temporarily spread across the old lake surface and drain toward that structural boundary, where runoff meets faults, cracks, and concealed karst features. Concentrated flow may wash fine sediment downward. And the same rainfall that appears to refill a dry surface for a few days can load the cover and accelerate the transfer of material into hidden openings. This explains why a wet spring can raise collapse concern after a dry winter, and the drought lowers groundwater and weakens the long-term system. Later rainfall adds weight and creates short-lived flow-through fractures. The two conditions are not opposites. They can act at different stages of the same failure process. And faults add another layer. The 2026 basin-wide reconstruction found sinkholes preferentially arranged in tight clusters along fault zones. And the authors linked some of that pattern to deep hypogene karstification, where fluids and gases rising from depth can renew the ability of groundwater to dissolve carbonate rock. That mechanism does not replace agricultural overpumping. It explains why the geology is uneven, why some corridors contain many cavities, and why neighboring fields with similar irrigation histories can behave very differently. So the hidden mechanism has three scales. At the smallest scale, grains fall into a void and a roof progressively fails. At the middle scale, groundwater decline and subsidence reshape stress and flow across farms and wetlands. At the basin scale, faults and rock units determine where soluble pathways and old cavities are concentrated. This is also why maps based only on drought or well density are not enough. A field can be dry without sitting over a dangerous cavity. A cavity can exist without collapsing this year. A known sinkhole can be stable at its visible rim, while another weak zone develops nearby. The strongest maps combine the evidence: geology, faults, groundwater behavior, topography, past sinkholes, surface deformation, and field verification. They do not eliminate uncertainty. They make it spatial. And in central Turkey, that spatial pattern is beginning to extend beyond the places where people learn to expect it. The phrase new sinkhole field can sound as though the land suddenly entered an entirely new geological era, and the record is more complicated. Central Anatolia has ancient obruchs hundreds of meters wide, formed through natural karst processes long before modern pumping. The younger cover collapse sinkholes are generally smaller, more abrupt, and closely associated with the altered groundwater system of recent decades. That difference matters because old and young sinkholes can occupy the same landscape while telling different stories. And the giant historic depressions show that the rock has always been capable of forming voids. The new holes show that human pressure and modern water loss are changing how often the shallow cover fails and where that failure appears. One 2025 machine learning study used a regional inventory to map susceptibility across Konya. A 2026 follow-up analyzed 495 sinkholes, documented from 2008 through 2025, and emphasized the strong spatial clustering of the hazard. The models identified areas where combinations of conditions resemble places that have already collapsed, and their value is not a colorful map by itself. Their value is deciding where to inspect, where to limit exposure, and where a subtle deformation signal might deserve urgent field work. And that work is moving toward early warning, but the phrase must be handled carefully. A sensor system may detect subsidence, cracking, soil movement, or changes in groundwater. It may reveal that a zone is becoming less stable. It cannot guarantee that every collapse will provide a long warning, and it cannot assign an exact collapse time to every suspected cavity. The reason is physical. Some roofs deform gradually and produce a measurable sag, and others retain strength until a relatively small section fails, after which the collapse propagates quickly. Agricultural machinery, irrigation, heavy rain, or ordinary surface loading may be present at the time, but the critical weakness can already be buried several meters below. Monitoring therefore works in layers. Satellite radar is useful for measuring slow deformation over large areas, but it cannot see the exact shape of every cavity. Electrical restivity surveys can identify contrast between intact ground, loose fill, and void-like zones. Seismic methods can detect changes in stiffness. Boreholes provide direct evidence, but only along narrow lines and at greater cost. The strongest assessment combines several methods and then checks the result against known geology and collapse history, and even that combination produces probabilities, not certainty. A dark anomaly in a geophysical section may be clay, wet sediment, fractured rock, or a cavity. A smooth radar signal may miss a small roof that fails abruptly. Early warning is most realistic where deformation is progressive and monitored continuously. Elsewhere, the best available warning may be a susceptibility zone, new cracking, a sudden sag, or a change in how water disappears from the surface. This unpredictability has entered daily life. Reuters documented fields near Karapunor with more than 10 sinkholes packed into one area. One farmer described 2 collapses on his land within 2 years. His brother was working nearby when the second opened in August 2024, with a violent rumbling sound. Geologists later identified 2 additional zones where sinkholes could form, but could not say when. No casualties were reported in that account, and the absence matters. It prevents a serious hazard from being falsely narrated as a mass fatality disaster, yet a lack of deaths does not make the risk abstract. Any collapse can take farmland out of production, sever an access route, threaten a well or irrigation line, and place workers near an unstable edge. The physical danger often extends beyond the dark circle visible from above. A sinkhole rim can continue to retreat as unsupported blocks fall from the sidewalls. Nearby cracks may mark a wider disturbed zone. Beneath the surface, The cavity or loosened material may extend beyond the apparent boundary. That is why dramatic footage of people standing at the lip can be so misleading, and the clean edge looks solid, precisely because the failure has cut it sharply. Roads and buildings raise the stakes, but they also demand restraint in the way the story is told. The mapped sinkholes are concentrated mainly in agricultural land, and this is not evidence that central Turkey's cities are about to fall into the ground. It is evidence that a major agricultural basin contains active collapse corridors, that some new zones are developing outside the traditional core, and that infrastructure planning must account for a hazard that is highly local. Same restraint applies to another discovery beneath Konya. Geophysical research has shown that the basin is slowly subsiding within a broader rising Anatolian plateau, possibly related to deep lithospheric processes. That is a fascinating piece of earth science, but it should not be used as the direct cause of an individual farm sinkhole. Deep mantle-driven basin evolution and shallow cover collapse operate on different scales. Combining them into one dramatic mechanism would create a story the evidence does not support. And the real cascade is already strong enough because water demand lowers the aquifer, while compaction and altered flow deform the surface. Faults and soluble rock focus weakness, fine sediment migrates into cavities, and eventually a roof fails. And the visible hole removes land, changes drainage, and concentrates fear around every new crack. Then the response begins. Officials survey the site, place barriers, compare it with susceptibility maps, and decide whether nearby land requires geophysical testing. Satellite radar continues measuring broad deformation, and researchers update inventories because every new collapse improves the ability to recognize the next high susceptibility cluster. In 2025, Konya officials reviewed the sinkhole issue as both a disaster risk and an economic and social problem. NAFAD's mapping work, which began earlier in the decade, was being combined with municipal investigations and monitoring. The Provincial Risk Reduction Program also described an early warning project that had expanded to include Karaman and Aksaray, and by May 2026. European Union-supported Resilient Karatai initiative was presented with the goal of improving early detection of sinkhole formation. Those programs are not proof that collapse is accelerating this week. They are proof that the hazard has become persistent enough to require organized monitoring across jurisdictional boundaries. And that leads to the midpoint reframe. The terrifying part is not that hundreds of holes appeared without any pattern. The useful discovery is that they do have a pattern, imperfect, clustered, measurable, and increasingly visible from space. Once the pattern is visible, the question changes. It is no longer, can anyone stop every sinkhole? The honest answer is no. And the better question is, can the basin reduce the conditions that make collapse more likely, and can it keep people and infrastructure away from the most susceptible ground? The first half of that question is about water. Groundwater decline is not simply a geological measurement. It is the accumulated result of crop choices, irrigation efficiency, rainfall deficits, well regulation, energy costs, and the decisions of thousands of farms. Closing one illegal well does not refill a basin. Installing one sensor does not restore pore pressure. The response has to operate at the same regional scale as the extraction. The 2025 groundwater governance research described a basin where licensed and unlicensed wells coexist and where policy contradictions can sustain water-intensive agriculture even as scarcity deepens. It also noted promising investments in monitoring and smarter irrigation, and that is a difficult conclusion because it offers no cinematic fix. The ground will not recover on a television schedule. Some compaction can be permanent. Once fine-grained aquifer layers compress, the storage space that held water may not fully return. A rising water table can reduce future stress without lifting every subsided field back to its former elevation. Likewise, reducing pumping can lower one driver of collapse without removing cavities that already exist. And the second half of the response is about learning where those cavities and weak zones are most likely to matter. NAFAD's susceptibility project classified sinkhole types, updated geological boundaries, incorporated structural hydrogeological boundaries, incorporated structural hydrogeological meteorological human factors, and used geophysical measurements and drilling in selected districts. The goal was not to produce a map that says safe or doomed. It was to build a basis for action plans. A high susceptibility zone can change a road alignment, the placement of a building, the route of a pipeline, or the intensity of site investigation. On farmland, it can guide where heavy machinery should not travel after new cracks or sagging appear. Around a known collapse, it can support a wider exclusion area than the visible rim alone might suggest. And there is also a scale problem in public policy. The highest risk zones may be narrow, but the water decisions that influence them are basin-wide. A municipality can fence a crater. It cannot by itself rebalance an aquifer shared by agriculture, industry, wetlands, and growing communities. And that requires measurement, enforcement, crop, and irrigation choices, and enough economic support that farmers are not asked to absorb the entire transition alone. The monitoring program is valuable partly because it can prevent the opposite mistake, treating every hectare of the basin as equally dangerous. Better maps can focus expensive subsurface surveys on the corridors where faults, previous collapses, thin cover, and measurable deformation overlap that allows roads and facilities to be evaluated site by site instead of relying on fear or false reassurance. The newest research adds a practical shortcut. Because recent sinkholes tend to occur near earlier ones, the existing inventory can guide surveillance while more complex models are refined. And that does not mean every hole will produce another within 500 meters. It means past collapse locations carry information about fault corridors, cavity networks, cover thickness, and groundwater pathways that are otherwise invisible. And this is where the phrase, "the ground is still collapsing," becomes precise. It refers to three things happening at once. New abrupt holes continue to appear. Existing rims can enlarge after the first failure, and broad areas such as Sinkhole continue to subside at rates detectable by satellite. These are connected expressions of instability, but they are not identical events. The rate history also prevents a false conclusion. The basin-wide inventory found fewer new sinkholes per year since 2019 peak. Researchers proposed that some of the most collapse-prone cavities may already have failed, reducing the rate in certain zones even while groundwater continues to decline. Another 2026 study described an accelerating formation problem using a different inventory and time window. Both can be true if they measure different places, definitions, and periods. The safest narration is therefore not that every year is worse than the last. It is that the hazard expanded dramatically over the past 2 decades, remains active, and is migrating or emerging in some areas that had little previous history of cover collapse. That is exactly what makes Sinkhole so important. And the former wetland is not merely another dot on the map. It shows how a landscape can cross from broad subsidence into localized failure when dried sediment, faults, runoff, and groundwater change meet in the same place. The ground does not need to open everywhere. It only needs one weak roof beneath one working. There is no verified warning that a specific town in central Turkey will be swallowed next. There is no scientific basis for a countdown. There is also no basis for treating the hundreds of mapped features as harmless curiosities. The hazard sits between those extremes, and scientists can watch millimeters of motion from orbit. Engineers can test the subsurface with electrical, seismic, drilling, and radar methods. Water managers can track wells and aquifer decline. Local authorities can update risk maps and land use decisions. And farmers can report new cracks, depressions, or sudden drainage changes rather than assuming the surface will hold. But none of those tools changes the central physical truth. A sinkhole becomes visible only after support has already been lost below. That is why the final image is not a giant crater by itself. It is a drone view of a geometric agricultural plain, irrigation lines crossing brown and green fields, and several dark circles breaking the pattern. Between those circles, the land looks continuous, but satellite radar says parts of it are moving, and ground surveys show the holes clustering while water records show the aquifer falling. The map is becoming clearer before the ground becomes stable. And central Turkey is not opening as one endless void. It is developing an expanding network of collapse zones across a stressed basin, with new fields joining old clusters and slow subsidence connecting events that once looked separate. The next sinkhole may still arrive with little warning. The larger field no longer does